Power Series Part 1 – The Basics. A power series centered at x equals c, or sometimes we say about x equals c, is an infinite series of the form sigma n runs from 0 to infinity of bn x minus c to the n. The first few terms are going to be then b sub 0 plus b sub 1 x minus c to the 1 plus b sub 2 x minus c to the power of 2, and many more. A power series is an infinite polynomial. The variable is the x, and the coefficients are the bn's. All power series are convergent at least for one value of x. We check that this value of x is exactly x equals c. It's the center of the expansion. We are going to substitute c for x, and we see that all the terms but the first one are now going to be 0, and we get only b0. Asking if a power series is convergent or divergent is meaningless because it is always convergent for at least one value. Rather, we should ask for which value of x the series is convergent, for which value of x it is divergent. We say that the given power series is centered at x equals c because the values of the x's for which the series is absolutely convergent are within equal distance from the center x equals c. Outside of this interval, the series is divergent. Let's see. Here is the x-axis, and here is the center of the series x equals c. We are drawing a circle that is centered at c. This is the radius. If we are looking only on the x-axis, we get the two endpoints, and the endpoints are c minus r and c plus r. The series is absolutely convergent for all x's in the interval c minus r, c plus r. The series is divergent on the segment that is outside that. Okay, so we have two segments like those. One is from negative infinity to c minus r, and the other is from c plus r to infinity. There are two extreme r's. One extreme case is when r is infinity. If the radius equals infinity, then we will get actually all the values of the x's. In this case, the series absolutely converges for all x's. The other extreme is when r equals 0. So if the r equals 0, it means that the series absolutely converges only for the value of x equals c. Obviously, in this case, it's going to diverge for all x's which are not c. Theorem. There are only three possibilities for which the series sigma runs from 0 to infinity bn x minus c to the n converges. 1. It absolutely converges only for the value of x equals c. 2. There is a positive number r such that the power series absolutely converges for all x's such that x minus c in absolute value less than r, and diverges for all x's such that x minus c in absolute value greater than r. It may diverge or converge when the absolute value of x minus c equals r. 3. It absolutely converges for all x. Let's again observe the three cases of the theorem. We will start with the two easy cases. The series absolutely converges only for x equals c. It diverges for all other values which are not x equals c. In this case, the interval of convergence, it's going to be just one point, x equals c. This is this case. So obviously the radius of convergence is now going to be 0. The other extreme is that the series absolutely converges for all values of x. In this case, we should include in the interval all real numbers, so we will get negative infinity to infinity, and the radius is infinity. The more complicated case is this one. The series absolutely converges only for x's such that x minus c in absolute value less than r, and diverges for all the value of the x's for which x minus c in absolute value greater than r. In this case, the interval of convergence contains all the numbers between c minus r and c plus r. The problem here that we need to check the two endpoints. The two endpoints are going to be obviously x minus c equals plus minus r. Each one of them may diverge, converge, absolutely or conditionally, I have no idea. In this case, obviously, r is finite. This is the picture of the interval, but again, I have no idea what's going on in the two endpoints, and I will need actually to check each one. What I know for sure is that the series is absolutely convergent between the two endpoints, and I also know that the series is divergent outside of this interval. For simplicity, I am identifying the term in the power series with an. We start by applying the ratio test or the root test. Observe that the limit is with respect to n, but the an's are expression of x. So L is going to be some expression of x. I would like L to be less than 1, because for all the values of x for which L is less than 1, we know that the series is absolutely convergent. We are going now to find R, the radius of convergence, using the inequality L less than 1. We are going to do algebra, which is usually very simple, and we will figure out for what R, if L is less than 1, we can get absolute value of x minus c being less than r. We are going to have three cases: r equals 0, or r equals infinity, or r is a finite number. Now we are ready to find I. To find I, the interval of convergence, we have to find the interval that contains all the values of x for which the series is convergent. By the way, not always absolutely. In the endpoint, it's enough just for the series to converge. We know that when the radius is 0, the interval is just the point which is the center of the expansion. When r is infinity, we know that I is the set of all real numbers. When r is finite, then we have to check the endpoints, and the solution will be one of these four possibilities. In the first one, none of the endpoints are included, and then we have that one of the endpoints is included, and then both are included. The end.